Hi, everyone. My name is Vipul Raheja. I'm an applied research scientist at Grammarly. I'm based in San Francisco, and I'd like to welcome you to our Grammarly AI-NLP Club meetup. Uh, this series brings together international leaders and specialists in AI, machine learning, and natural language processing to share our research content and to share their research content and learnings. And today I'm joined by my amazing colleagues and teammates, Dhruv Kumar, who's an applied research scientist, Robyn Perry, analytical linguist, and Apurva Joshi, software engineer, with whom I work together to build Voice Composer, Grammarly's latest generative AI-powered feature for mobile. So before we get to the main reason for gathering here, let me share a few organization details. So during the presentation, you can submit any questions you have during the Q&A feature in Zoom, and our speakers will address those after the talks. So let's get started. So to kick things off, I'll talk about the big picture, what Voice Composer really is internally, which is the what of it, and also shed some light on the how and why we built this. So first, in case you're not a user of iPhone or have not used Voice Composer before, here's a short demo of what it is.
Please write an email to John and apologize that I won't join the project review meeting today. And I will appreciate if you can record it. I will follow up with you on updates and action items tomorrow. And looking forward to meeting you later this week. Thank you, Igor.
So as you can see, Voice Composer is powered by advanced speech recognition and generative AI and allows you to convert conversational speech into polished and accurate compositions. Additionally, to help unblock ideas, users can simply ask Voice Composer to create a draft for them with a short prompt, such as write a blog post about the Grammarly keyboard for iOS and so on. And Voice Composer will use that and generate a coherent and clean piece of text for you. So why did we build this? Or what's the motivation behind putting generative AI to mobile? In order to understand that, we need to understand the typical writing process and how Grammarly has helped users with it. The first step is the ideation phase, where the writer generates ideas, gathers information, explores potential topics. The second step is planning, where the writer will create an outline or structure for their writing. This serves as a roadmap and helps everyone organize their thoughts. The next step is the drafting stage, where a user will write the first draft. They'll begin writing their content based on the outline or plan. And during this stage, they'll focus on getting the ideas on paper without worrying too much about grammar or perfection. The next step is revision, where one reviews and revise their drafts for clarity, coherence, and flow. Check their writing for errors in spelling and so on. Finally, there's a stage of editing where, based on the feedback and their own analysis, people will rewrite entire sections and perform major structural changes and minor adjustments to get it ready to send. And finally, once all of these steps have been taken, the piece of writing is ready to be sent. And more broadly, this can be divided into two parts. One is composition, and the other one is revision. And historically, Grammarly has helped users in the revision stage of the writing process. Of course, that has now changed with Grammarly Go. But when we started working on this, that was the main motivation. And finally, to help users with composition, it was what really motivated us to work on this, as that is what takes a considerable amount of time and cognitive effort. So we gathered various types of product requirements by surveying and interviewing users. Typically, mobile phone users and voice-to-text users, and understood that the product should support various features. The first one is what writing application does it support? Email, messaging, notes. The second one is what kind of input mode should we support, instructional or dictation, which is what you see here. And finally, what's the level of information that should be contained in the input? Should it be open-ended or closed-ended? So here are a few examples where the first one, you can see it's an instructional input for writing an email, and it's closed-ended because it has all the information that's needed. Whereas the second one, you can see, is also an instructional input, but for writing a blog post, which is kind of like notes, but it's open-ended, and so on. So why did we make these decisions to support voice, and why did we make this decision to support this on mobile? So for the first one, we realized that voice is a natural mode of communication for people. Users are familiar with voice assistants, and acquiring user input is much harder through other means. But because voice just comes naturally to people, it's just easier. And for mobile, again, people are really familiar with the medium thanks to Grammarly keyboard that already has been out there for a few years now. And again, related to the last point for voice, typing or editing on mobile keyboard is relatively difficult. So we wanted to make that easier. And finally, smartphones are the largest and fastest growing mode of communication. So that was another big reason why we chose to go on mobile. So here's an overview of how our system works. Firstly, the user will give their input in the form of an audio. It'll go to an off-the-shelf speech recognition service, which leads to the transcribed format of this voice input to be converted to text. But as you can see, it'll contain a bunch of different issues. Then this transcribed input will go through a normalization stage, which further consists of 3 other substages. And we'll clean it up, clean up the speech recognition errors and so on, and try to get it to a much more refined form. And finally, this processed input will go through the comprehension stage, where finally we will generate the cleaned, well-formatted output. And now I'll go through details of these, some high-level details of these stages. So the first one is automatic speech recognition, whose responsibility is the transcription of audio input to text. It is the entry point to our system, and it handles basic speech recognition errors such as filler words and background noise. And the way we implemented it was we just leveraged out-of-the-box ASR, or automatic speech recognition solutions. We experimented with different speech-to-text services from Microsoft Azure, Google Cloud, and OpenAI Whisper. But in general, we found that in Google and Microsoft Azure are all kind of at par in terms of supported features. We also considered OpenAI Whisper since it's open source and about 70% cheaper. And finally, we evaluated them using word error rate and word recognition rate, which are standard evaluation metrics for speech recognition. For the second stage, which is normalization, the main idea is to recover from speech recognition errors that we find in the transcribed audio, because it can still contain noise because of different reasons, such as speech recognition errors, disfluencies, uniqueness of people's way of talking, such as different accents or utterance speeds and so on. Word boundaries can be ambiguous and so on. And this stage essentially enriches the speech transcription further and gets a cleaner output, cleaner input for the comprehension model downstream, as you can see in the figure. And as I had mentioned before, there are 3 substages dedicated to addressing these specific issues in the transcription. The first one is speech disfluency filtering, whose job is to detect and remove disfluent tokens. So in this example, you can see there's a bunch of filler words and false starts, which this stage removes. The next stage is punctuation restoration, whose job is to restore punctuation, including capitalization, to this disfluency filtered text. So you can see there's capitalization and some punctuation being added. And finally, we send this text through a stage of grammatical error correction, whose job is to fix any fluency errors in the input, as you can see here. And then how we did it was we implemented 3 fine-tuned token level sequence tagging models for each of these stages. All of these models are trained on a mix of internally sourced and publicly available data sets. For the first one, the speech disfluency filtering, we fine-tuned a Roberta model on data which was augmented by adding artificial disfluencies using this paper from Google. For the second stage, punctuation restoration, we used a Distilbert model, again on data augmented by adding artificial punctuation on different domains. And finally, for grammatical error correction, we used another Roberta model augmented by large-scale in-house grammatical error correction corpora. And in terms of what we found that speech input is really convenient for the user, but it comes with a lot of issues. And as a result, we have to implement this multi-stage pipeline in order to do the cleanup for the generation stage downstream. We found that disfluency filtering is challenging because of the spontaneous nature of speech, and it's even harder for streaming use cases. And the reason why we formulated these as sequence tagging problems was it's beneficial for future joint modeling of all of these with possibly a single model. So let's talk about the comprehension stage now. Finally, after going through all these stages and getting cleaned up, we send this cleaned up input to our comprehension models to generate a structured and coherent output. And the input, as I mentioned, can be of various types: instruction, dictation, email, IM, and can contain different levels of information. And our solution to this was using 2 different models. One was an in-house fine-tuned large language model. Another one is an external large language model. And we use both of these in combination. And here's how. So when this cleaned input text comes in from the normalization stage, we send that to an input classification model, which is again a Roberta-based model, and it will orchestrate which comprehension model this input text should go to. Should it go to our internal fine-tuned model or to the external LLM? Our internal fine-tuned model is it was originally trained for summarization, but we fine-tuned it for rewriting in our case. And the comprehension LLM, which is the external LLM, is a GPT-based model for composition. And in terms of what we learned, the biggest learning here was that balancing trade-offs between accuracy and efficiency can be very challenging because user preferences can evolve. We found that initially users were more interacting with the system in a dictation style, but then eventually gravitated towards more instruction style. So we had to adapt accordingly. And because of this change in user preferences, it affected our development as well, because we needed to adapt data, model training, and our evaluation frameworks. All of these things Dhruv and Robyn will talk about. And the second thing was that in-house comprehension model was better at meaning preservation, which is ideal for short, mobile-heavy use cases like text messages, notes, short emails, and so on. And finally, we also the reason we included the external LLM was because it was better at handling open-ended inputs, which is ideal for longer, more creative inputs, such as composing new emails, documents, and so on. So to sum up, here's a bunch of different challenges we face and learnings we had. One of them was that finding the right product experience is really critical. So in order to do that, we had to go through a lot of iterations and user studies. We tried Voice Composer on multiple surfaces, applications, target audiences, and so on. And finding that was critical to for us to improve the technology underneath and ensure users have a great experience. Another challenge was to figure out how do we bridge the gap between user experience and modeling this text generation, because as I mentioned, we had to keep adapting according to user needs. But another aspect to it was sometimes there was a lot of subjectivity in evaluation and what people really wanted to do and what they were getting, and how to strike a balance between our models preserving the meaning of the text versus being creative and paraphrasing, and how do we set the right tone and so on. And finally, again, something which both Dhruv and Robyn later will talk about, our challenges on evaluation. How do we handle errors that appear earlier in the pipeline and keep cascading through the pipeline? How to handle model sensitivity to minor changes and so on, and how to make it more robust. And again, how to handle automation trade-offs in evaluation. So with this, I'd like to give it to Dhruv, who will talk more about our in-house comprehension model.
Awesome. Thanks, Vipul. Hi, everyone. So I'm Dhruv, and I'm also an applied research scientist at Grammarly. So what I'll be talking about today is the in-house comprehension model, which we call the comprehension FT. Vipul, next slide. So to start off, let's revisit the requirements as to like what capabilities or what tasks this comprehension model should be able to do. So the first is that, as Vipul mentioned, it should be able to work on like standard instruction-based inputs as well as dictation-based inputs. The second thing is that it should work on a variety of use cases. So for example, emails, notes, as well as like short-term messages like IMs, chat, or search, because people can use, basically this anywhere and any application on their mobile. The third thing is that the real world data has a lot of noise. So this model should be able to handle these noise. So we have previously in the pipeline models that handle this noise, but this should be able to handle the remaining issues if they exist, or any new issues if they are introduced by the previous models. Then it should ensure that the final output is correctly formatted. It's free of issues like GC and stuff. Then it should be able to work for both short and medium size inputs. So for this particular iteration, we contained ourselves to short and medium inputs and not so much long inputs. So we cap both the inputs and outputs in our model at 512 tokens, which is roughly like 300 words. And finally, as I said, it should maintain high grammaticality. Coverage, it should be true to what the user has said, and it should be natural. So, so it should look like that the output ideally is written not by a machine. It should look like that some human might have written this. Next slide. So a solution for this is that we fine-tune a sequence-to-sequence model. And we fine-tune this on an in-house data set that I'll talk about how we created, which handles like a lot of these cases. And basically, we collect that data set using both manual and automated methods. Next slide. So now let's first talk about the data set. And to create this data set, there are basically 3 steps. So the first step is human annotation. So we ask humans to give us some input-output instruction-based pairs, covering use cases such as emails and notes, and both instant messages and chats. So we have 6,000 instruction-based pairs, which contains emails and notes, and 1,000 input-output pairs containing shorter messages such as IM and chat. So in total, 7,000. Next slide. The second step is we take these human annotated input-output pairs, and we first polish the outputs. So basically, we ensure that the formatting is correct. We fix any errors, for example, any naturalness errors, or for example, any grammatical errors. We fix those things. And then we also polish the output by basically paraphrasing it so that it sounds more natural, and the quality of the choice of words are ideal for the type of message that the user is saying. And then using this, we generate the dictation data set, and I'll talk about how that works. So because we want to handle both instruction as well as dictation, from this instruction data set, we automatically create a dictation-based data set. Next slide. Finally, we talk about robustness. So the idea is that when people actually speak, there's a lot of noise, and we want the model to be able to handle those different types of noise. So we want our training data set to mimic that noise, and therefore we augment our data set to artificially add this noise. Artificially add this noise so that the model learns to be able to deal with it. Next slide. So finally, once all these 3 steps are completed, we end up with 28,000 pairs for training, which includes 14,000 instructions, 12,000 dictation, and 2,000 pairs for short messages. Similarly, for validation set, we have 600 pairs, and for test set, we have 2,000 pairs. So one thing to notice is that we start with 7,000, close to 7,000 input-output pairs, which the humans annotate, and we end up with close to 30,000 pairs. So we basically multiplied by 4x, by these artificial automated methods, which I'll talk about. Next slide. So now let's talk about how this entire pipeline of data set creation works. So at first, we have the input. So now this input could be a note, it could be an email, it could be instruction-based, it could be dictation-based. But for this case, we take an email and we take it as an instruction. So the input is that send an email to Luke and tell him that I've located the suspect. In this case, tell that I have taken the photos of the suspect in London while on vacation, and tell him that due to lack of access to the system, I cannot enter the data. Ask if he can help and thank him at the end. So it's an instruction to write an email. Next slide. So now when the humans annotate, this is what we get, which is Luke, I've located suspect, and it's basically copying it, just changing from third person to first to second person, depending on the case, and then it's addressed to Luke. So it's basically an email, right? So that is what we get as the original annotated training pair. So you have the input and you have the annotated output. Next slide. So once we apply the step 2 that I talked about, which is the enhancement stage. And now if you look at the enhanced output, it is much better formatted. The grammatical errors are fixed. And then you see that a lot of the words and phrases are changed to basically be a bit more natural and a bit more polished, right? So we apply paraphrasing on top of this annotated output to get this enhanced output. So the final output, which is the rightmost email, that looks much more of an email than the middle one, which we initially got. So now with this process, we get these 3 stages. Now, if you take the input and you take the enhanced output, that we use as the instruction email pair. So to train our models, we take the input and the enhanced output, right? And that can be used to train a model to generate emails for a given instruction. Next slide. And then when we follow this process, we also automatically get the dictation email pairs, because you can use the annotated output as a proxy for dictation, where there might be no formatting, there might be noises, it might be grammatically incorrect, and there might be a need to even actually paraphrase what the user said, to improve it. So the annotated output and the enhanced output can be used as dictation email pairs. So now you see if we get instruction pairs from the humans, and we are able to, through this pipeline, generate both instruction email pairs as well as dictation email pairs, which we use for training a model. Next slide. So now let's talk about the third stage, which is the robustness. Now, the first question is, why do we need this stage? So the idea is that this original data that we got was very clean. And real-world inputs, when people actually speak like I'm speaking now, that's in spontaneous speech, there are different types of errors that occur. So we in the initial pipeline, we have some models that fix some of the errors, but we have intentionally tried to build the system a bit redundant, so that if there are some errors which were not fixed, or maybe some errors which were introduced in the earlier pipeline, this final model is able to fix all of this, and the final output is much cleaner. Next slide. So the way we do this is we basically artificially augment this data set to introduce these real world noise use cases. And we built on this library called NL Augmenter. So it's an open source library which came out around 2020, 2021, which has multiple different types of noise-based augmentations. So we use some of those augmentations, but we also add some new augmentations on top of it. So in total, we end up having over 20 augmentations. And through these augmentations, we handled 4 different types of issues. And in the end, we end up creating more than 10,000 new data points for our models. Next slide. So now I'll talk about some of the augmentations that we create to handle some of the issues. So the first is homophones. So homophones are words which are similar sounding, but they obviously are different words. So sometimes, when due to accent, for example, the ASR models can actually, switch words. And this can be hard for the model to actually fix. So what we do is we take some random words and swap them with their homophones, which are similar sounding words, in the input, and the output remains the same. So the model actually learns to, in case there is a mistake made by the ASR model, it fixes in the output. Next slide. The second is the normalization issue. So Vipul talked about, how we deal with filler words such as and also punctuation removal. But this is again another step that we do. We wanted to give the comprehension model also the ability to handle these cases, because just in case there is some issue earlier, this model finally is able to, fix those things as well. So we have filler words and punctuation removal. Next slide. Then we have the noisy user input, right? So when people speak, for example, a lot of times they repeat the content, right? So this repetition might be at the level of sentences, or it might be at the level of words or phrases, right? So in case people repeat some stuff, the model should know, that there is some repetition going on, and it should fix it. And also it should know where to remove information, because if I say some information twice, maybe there is a specific place, maybe the second time that I said it, that's where it's more appropriate. So that is where it should keep it, and it should remove it for the first time, right? So these decisions need to be taken by the model. The second is when people speak, they can randomly skip words, they can randomly insert words. For example, prepositions are very good use cases where people actually do this, and the model should be able to fix these cases. Then when people speak, a lot of times the ordering of sentences is not ideal, which results in very incoherent input, and the model should be able to readjust the sentence ordering and stuff like this to fix these use cases. Next slide. Finally, we have the sensitivity issue. So we know that when these models, when they generate text, they are very sensitive to little changes in the input. So for example, if I change a name from a Western name to a non-Western name, the model, for the same content, the model might behave very differently. Or for example, if I change, let's say, pronoun, right, then again the same thing might happen. So to fix these cases, we basically ensure that within our input, all these different use cases are covered. So when you make these small perturbations to the input, basically, and keep the content exactly the same, the model behaves consistently for everyone ideally who uses this model in that sense. Next slide. So finally, I'll talk about the evaluation. So now evaluating these generation models is very tricky, and you need to cover a lot of bases, to get a complete picture. So in this work, we actually looked at 5 different types of evaluation. So the automated metrics, which are like mostly n-gram based metrics. The problem here is that even though they are very quick to get results from, they are not very reliable, because, for example, we do some paraphrasing. So when you start paraphrasing, n-gram metrics start to fail, but nevertheless, we did use it in the initial part. Then we have some human judgments, where this is the most sort of, it's the best way to actually get some sense of how the model is performing, but it takes time. So then we have some black box metrics, where it's mostly like rule-based entity checkers to basically see if how true the model is, how true the generated output is to the original input. Then we have golden metrics, where we looked at specific product use cases, and then we have the sensitivity risk evaluation. So in this talk, we'll talk about the first 2, and I'll be covering the automated metrics. Next slide. So to initially look at the models, we went through these bunch of models. Now, one thing which is very sort of directly noticeable here is that most of these models are very small models compared to today's standards. So from 240 million parameters to 1.3 billion, and this was intentional. So we wanted, because this in-house model was supposed to look at only some very specific use cases, we wanted to optimize for the speed or the latency of this model. So that's the reason we kept this model as small as possible while covering most of the use cases. So we looked at a bunch of model, and then we evaluated using these n-gram metrics, which I talked about, the Blue, Rouge, Meteor, and Blur. And what we basically found, a bit surprisingly, is that the Pegasus model, which is a summarization-based model, actually works better than something, say, like BART or even T5, which were models which came a bit later. And therefore, for most of this work, we just stuck with Pegasus and did most of analysis, which Robyn will talk about on this Pegasus model. So with that, I'll hand over to Robyn, who will talk about the human evaluation part.
Thanks, Dhruv. Yeah, hi, happy to be here. I'm Robyn, and I'm an analytical linguist at Grammarly. I'll take us through the evaluation portion of the talk. Next slide. So first, I'll give you a quick moment to look through this text. You'll notice a few things are wrong. Next slide. So we see punctuation errors, capitalization in the middle of a sentence, coherence errors or things being out of order, some unnatural text like "have a good day" and "ask if you are okay." And after emphatically thanking you, that also sounds a bit strange. And then a classic grammatical error, "I will not being so busy during this period." And finally, "which makes our interaction feasible," sounds a little robotic. So there's a lot wrong here. And our job with the human evaluation was to ensure that our model doesn't generate stuff like this. Thanks. This may be an extreme case, but you'll see that it was important to consider all kinds of errors. So I'll take you through our evaluation framework. So we know the why. Why do we evaluate in this way? Now let's look at what we evaluate. Next slide. As my colleagues have talked about, we've used both in-house models and worked with external LLMs to see how they compared against our own models. So we needed a framework that would help us consistently measure both and how they are performing, how they're stacking up against each other, what their particular strengths and weaknesses are, and which we would ultimately choose for our pipeline. Next slide. So as Dhruv covered, we have a whole mosaic of evaluation techniques. I'm going to make the case that human judgments are the most important. And I'm only going to be talking about the human benchmarking that we did, meaning that the evaluations over time that let us see how our models were changing over time with a standard set of evaluation criteria. We did all kinds of other human evaluations, which I could talk about, but if you have more questions later, but I'll cover just our benchmarking for this talk. Next slide. So human evaluation is absolutely critical. Humans are the end users. And so we need them to judge whether our outputs really make sense and work for the contexts that we're imagining with all of our test data. So human language is layered and complex. In every communication, there is tone, there's some kind of register, meaning a formality level. People have distinct styles. Communicators have a shared context when they're speaking to each other about something. There are also expectations based on the domain, the industry, or the type of event or interaction. There are relationship dynamics between the interlocutors, or that's the word for people speaking to each other. And then culture also dictates norms, communication norms. And there are even more things than I've mentioned here. So humans are incredible at quickly judging all of the above together effectively. And as we all know, we're not always perfect at communicating, but we know when something is wrong. So automated evaluation is very important for certain things, but it's too narrowly scoped to give the full picture of performance the way that human evaluation can. Next slide. So human evaluation, as I've said, is critical, but it sort of needs corralling and taming. We need a framework with definitions that are standard, and they standardize these subjective human judgments. Our evaluation dimensions need to be comprehensive. They need to cover all the cases that I showed in that very first slide. They need to complement each other. They need to be repeatable and measurable. Our models have to output something that sounds like well-formed native English. So we really have a high bar to hit. We also need to iterate on our evaluation framework so that we ensure that as things are changing, as user needs are changing, we are accounting for everything that needs to be measured. And so let me talk about our framework. I'll briefly cover these and then I'll give some examples following this slide. So grammaticality is the first and probably most objective. There are agreed upon conventions about what grammaticality means. Coherence is another important one. Is it well structured? Is there flow? Is there no redundancy? Or so is it well structured? Naturalness is a little bit kind of the most slippery one. Could it have been written by a native English speaker is the easiest way to capture it, but you'll see that some of the examples are very subtle. And coverage, finally, is really important because it measures whether the meaning and the content of the input are retained in the output. So we can't optimize on only one of these dimensions. We have to keep improving on all of the dimensions simultaneously, and we have to sort of hold them even or close to even to produce effective natural language output. Next slide. So I'll give some illustrative examples just so that we're all on the same page. Here's a text. I'm not showing the input text for these. I'll show just the output text. So, hey, so can you please send the form when you get a minute? This sounds very natural, actually, but there are some grammatical errors in it. We don't have a capital at the beginning. We need probably some more punctuation. There's an abbreviation without a period in it. So we hit the mark on all the other dimensions except grammaticality. Next. So this dimension allows us to ensure that the result is grammatically correct. Next. Here's one which you probably might recognize. It could be an output from an automatic speech recognition that went wrong. I'm David and I ate 2 questions. Please respond as soon as possible. We are short of cards. So this is not coherent. And I made a note that it probably doesn't have good coverage either because it probably doesn't match the original input. So coverage next lets us ensure that the result makes sense and is well structured. Sorry, coherence is what I meant to say. Next. Here's one where I'm trying to highlight naturalness. Congratulations to our best client, Becky, on her birthday. Best wishes. So this one's a bit strange. It doesn't make that much sense. So we have a problem both in terms of coherence and naturalness. But just to give an example, naturalness is, or a lack of naturalness is something like this: best wishes without an exclamation point. It's a bit cold if it's written that way. And then usually you'd say, congratulations to you on your birthday. So there's a pronoun problem that creates some naturalness issues. Would a native English speaker send this? Now, next. Yeah, thanks. And here I show also the input in blue. This is the coverage dimension where we want to ensure that there's no added information in the output that wasn't there originally, or nothing was lost in the output that should have been there originally. So I'm going to go to the market and will be late. Don't wait for me. Turns into, I'm going to the market. I'm going to be late. Don't worry about me. I'll be there on time. There's a hallucination there. The original speaker didn't say anything about being on time. And then the reverse of that is is the bottom where we lose information. My honest opinion is that she should come in for an intake appointment, then you can decide what to do next. My honest opinion is that you should come in. So pronoun is changed and then the last sentence is left off. So, or a piece of the last sentence. So I think that gives a picture, next. Coverage ensures that there's fidelity to the original input. Is anything lost or added? So I think that covers our dimensions. You can go to the next slide. As you see, they sort of function as checks and balances for each other. Benchmarking allows us to monitor the performance over time and sort of keep everything steady without optimizing too much in one dimension, because that can cause problems in another dimension. So I'll show now that trade-offs between dimensions surfaced as we handled more use cases. Next. So here's an example of two possible models that we might use, and maybe we have to choose between them. So our example is, hi, Pauline, is this some maps you produce and can send to Joshi? There's something strange about this output, but as Dhruv kind of alluded to, we have so much messy input, we have to decide what to do with it. So we've got model A, which is a little bit more aggressive. It rewrites this to say, do you have any maps that you can send to Joshi? This sounds more natural, but it may have changed the meaning of the original. Whereas model B, next, is a bit more conservative and retains one of the grammatical errors, but keeps the coverage probably a lot closer to the original. And we can show next slide. So similar here, I want to show an interesting trade-off where when we get into the kind of messaging area where you're doing instant messaging or something pretty casual, that the priority of dimensions can shift. So, hey, so can you DM me about the job app? Sounds very natural, has some grammatical issues. And model A output, again, is very aggressive. It rewrites it to be completely grammatically correct, but very formal and not really appropriate, probably, for what the person was originally intending. Whereas model B is a lot more conservative, retains some of the grammatical issues, but possibly would be preferred by the user, maybe, because it seems a lot more like something you would text. And maybe that's what their original intention was. Next slide. So I'll quickly talk here about some of the limits of human evaluation. This first piece is about subjectivity. So as you may imagine, when we give guidelines and we give a task for human annotators to make judgments, there can be a lot of variability between people. So that's what we call inter-annotator variability. And there can even be variability within a single person at two different points in time. So there's a lot of subjectivity that people that we contend with in order to get human judgments. There can also be errors, so a lapse of attention, perhaps the task design is confusing, or just misunderstandings. And then, as always with people, there's unavoidable bias of many kinds. I'm not even going into all the kinds of bias here. So what do we do to mitigate some of these issues with subjectivity? We test the task design and the guidelines very heavily. We build in iteration time and request feedback from our human annotators and judges. And we monitor the annotator agreement to check if there are any particular outliers or people who are really making pretty different judgments than the group. We always include redundant judgments so that it's a little bit more like a vote than a single person making a decision. And we focus on trends. We know that there are errors, so we have to focus on trends, and we perform quality checks to ensure that we can trust the results that we have. And we use sufficiently sized data sets so that some of that error and some of that bias can be washed out with the general trends. Next slide. And another limitation that's really hard to mitigate is resources. So human annotation costs time and effort and money. It's harder to figure out how to mitigate some of these issues, but I'll talk about a few things we have done. And then, but just to go through them, so guideline development takes time, recruitment and people management takes time, iterating on the task and the design of it, and then doing the analysis of the results, as well as just the human time of doing the task. So the hiring skilled and experienced people is really important part of making sure that this is done efficiently and well and at a high quality, at a high quality level. And then another thing that can be done is streamlining eval sets to decrease the turnaround time. So as we were using large test sets, we realized that we could shrink them down a little bit by making sure that we compared the results over several benchmarking rounds to trust that those smaller results were going to be representative of the larger results. And you can also do something like identify the most informative items in the evaluation sets and only have evaluators, human annotators, judge those. This might change the results because some of the easy ones will be missing, like easy as in some of the ones that annotators will agree with again and again will be missing, but it's an option if time is an issue. So with that, we can take questions later, but I'll pass it on to my colleague Apurva, who will talk about scaling up our project. Thanks.
Hello, everyone. My name is Apurva, and I'm a software engineer at Grammarly based in San Francisco. I'll talk about how we built, deployed, and scaled Voice Composer as a service. Next slide. Voice Composer is written in Python and deployed on AWS Elastic Container Service. As a service, Voice Composer supports 3 API endpoints. The first API endpoint is normalize. This endpoint takes a raw or transcribed text as input, removes disfluency, and adds punctuation to the text. This endpoint has a P90 latency of 30 milliseconds and uses transformer models like BERT for punctuation restoration and distill BERT for removing disfluencies. The second endpoint that the service supports is generate. This is the main endpoint that generates a well-formed text devoid of any grammatical errors based on user's instruction or dictation. This endpoint uses a combination of in-house model and Azure OpenAI to generate the text. It has a combined P90 latency of 2.4 seconds. And finally, there's a service endpoint to return speech-to-text token. We use Microsoft Azure services to transcribe speech into text. This token is used by mobile apps to authenticate and communicate with Microsoft Azure. This endpoint has a P90 latency of 50 milliseconds. Next slide. Next, let's look at a high-level architecture of how these endpoints are used by the mobile apps. When you use the Voice Composer on the Grammarly app, your mobile device sends a request to the backend proxy service to obtain a speech-to-text token. The proxy service, in this case, is a service that can receive traffic from the internet and handles authentication, authorization, and rate limiting, so that the Voice Composer service can focus on the business logic. The proxy service forwards this request to the Voice Composer service, which then obtains a token from Microsoft Azure's speech recognition service and returns it back to the mobile app. With this token, the mobile app can establish a direct WebSocket connection with the Azure service for live speech transcription. Having a direct WebSocket connection ensures that the speech is transcribed into text in real time without any visible delays. The speech-to-text token is valid for 10 minutes, so the mobile app requests new tokens every few minutes to ensure that it always has a valid token whenever the user starts speaking into the app. Up to this point, we saw how mobile apps convert user speech into text. Next, let's see how this text is transformed into a well-formed text using the other endpoints provided by the Voice Composer service. Next slide. Let's say the user speaks, "Ask John, how you doing?" into the mic on their device with some speech disfluencies. This text is sent to the backend proxy service. The proxy service in turn calls the Voice Composer's normalize endpoint. And if you remember from the earlier slide, this endpoint removes disfluencies restores punctuation, and sends the updated text back to the proxy service. So here, if you see the output text, it capitalizes the first word and the name John and adds a question mark at the end of the text. Moreover, it removes disfluencies like capture from the speech. Next, the proxy service calls other internal Grammarly services like grammatical error correction on the input text to fix grammatical errors. And finally, it calls the voice composer's generate endpoint with a grammatically correct text. Once the voice composer service receives the request, it runs a classifier on the request to determine whether the request should be served from our in-house model or through Azure OpenAI service. Any text with a close-ended prompt like simple messages and instructions are served via the in-house model, while open-ended prompts like write me a short story or write me a joke are sent to the OpenAI GPT model. Since in this case, the message is short and close-ended, it's sent to the in-house model, which generates the text based on the user's instruction as, hey, John, how are you doing? And returns it back to the proxy service. Notice that the generated text is also well formatted with the greeting followed by the new line and then followed by the body. Finally, the proxy service runs the generated text through a sensitivity service to make sure that the generated text does not contain any abusive words or sensitive language and sends it back to the mobile app. Hopefully, this gives you a good idea about the various steps a text goes through before it's fully composed and shown on the user's mobile screen. Given that the service goes through multiple steps, it's important that we optimize the service and make it work under a strict latency budget. Next slide. Let's look at some of the optimizations that we added to our service to make it more robust and work under a strict latency budget. One of the first things we did was to find the optimal instance type for hosting our service. We looked at various GPU-based instances that could be used for inference on AWS. P3 instances on AWS are the highest performing GPU-based instances, but they're also expensive. G5 instances provide the best value for money. They're cheaper than P3 instances, but they provide optimal performance for most machine learning inference needs. So we found that we can continue to maintain our SLA of 3 seconds using G5 instances at 5 times lower cost compared to P5 instances, while only trading off 1 second from our latency budget. So we decided to use G5 instances to host our service as it provides us with good latency and cost trade-off. Moreover, we increase the number of inference workers running on the instance for 100% GPU utilization. Unlike CPU, 100% GPU utilization is a good thing, and we should tune the service to ensure we are squeezing out all the performance from our GPUs. Next slide. We use the ONX runtime library from Microsoft that converts the native PyTorch model into ONX format and leverages the hardware accelerator to further speed up the inference. This is more for the model level optimizations that we wanted to perform. We found that ONX performs better than native PyTorch model at lower batch size, but the performance degrades as the batch size increases. Furthermore, increasing the beam size leads to slower inference on both PyTorch and ONX. The graph on the left is for beam size 4, and the graph on the right is for beam size 8. Here, x-axis represents the batch size, and the y-axis represents the latency. You could see that the latency increases as the batch size increases. Moreover, latency further increases if the beam size is increased, keeping the batch size constant. Next slide. We found that converting the model to ONX improves the inference latency by 23%, but at the cost of a 50% GPU utilization increase. In an online scenario, this means we are able to fit in less number of inference workers per instance, since they need to compete for the same GPU, which reduces the overall throughput of the system and undermines any latency benefits we get with ONX. So in the production setting, we decided to use the native PyTorch model using 2 inference workers per instance instead of using ONX optimization. This provides us with better latency performance at our desired throughput. A key learning we had here is that the optimization results that you get in an offline setting may not always translate well in the online environment, and you should always run end-to-end load tests to see the overall performance benefits. Next slide. So far in the talk, we focused on optimizing the latency for our in-house hosted model. If you remember from the architecture diagram earlier, we also use Azure OpenAI to power Voice Composer. Here we compared the performance of 3 different systems. First, a system based on only our in-house model. Second, a system based only on Azure OpenAI. And finally, a hybrid system, very much like a current production system, that comprises of in-house hosted model as well as Azure OpenAI. We look at the number of instances that these systems need to maintain a P90 latency of under 3 seconds. We find that we can use a single G5 instance to maintain our SLA of under 3 seconds using our in-house hosted model, thanks to all the optimizations on the service side and the model side. However, we need 30 instances, that is, we need to scale horizontally to maintain the same SLA using only Azure OpenAI GPT model. This is mainly because it's a much larger model, and moreover, there is a network latency involved in connecting to a third-party service. However, if we build a hybrid system that relies on the in-house hosted model for simple close-ended queries and uses OpenAI for more complex, rare queries, then we can reduce the number of instances to 12 while continuing to maintain our latency and throughput SLA. Next slide. So far, we looked at various optimizations that we could apply and compared different types of systems using in-house models and third-party hosted models. Next, let's look at a couple of key takeaways from this. If you're using an in-house large language model, then optimization is critical to maintain a strong SLA. However, model-level optimizations are not always additive to service-level optimizations. So always load test the service end-to-end to see the overall benefits of any optimizations you apply. Third-party hosted models like OpenAI GPT are great and can support many complex tasks. However, building a consumer-facing product using them is challenging, as these hosted models do not provide any strong SLA guarantees. However, using OpenAI streaming API, which outputs a few tokens at a time instead of returning all the text at once, can reduce the user's perceived latency, but it also adds additional complexity for downstream services to handle the streaming text. The best of both worlds is to use an in-house LLM to serve simple requests while delegating complex requests to third-party services like OpenAI. This ensures that we can maintain high throughput and achieve a low latency while still maintaining a very high quality bar. Thank you.